Thank you for having me here, and this is my pleasure to talk about my recent research in fact-based learning. So this is a paper I'm presenting, Complement Sparsification, Low Overhead Model Pruning for Fact-based learning. So this paper addresses a problem of model pruning for fact-based learning to achieve a low bidirectional communication overhead between the client and the server, and low computation overhead at the client, and achieve good model accuracy. The main idea of this problem is to have the server and the clients collaboratively and complementarily prune the models to create sparse models to capture the global data distribution and also the local trends at clients. So as we know, fact learning is to preserve the privacy by training locally on clients. So in traditional fact learning, we use dense and over-parameterized deep learning models. And this is because more over-parameterized models are easier to train. However, this over-parameterization comes at the cost of a significant memory, computation, and communication overhead. And this overhead makes it difficult to run fact learning on resource-constrained mobile and IoT devices. And therefore, it is essential to reduce the overhead in fact learning while maintaining the good model accuracy. So here, model pruning can be a potential solution to this problem. So in model pruning, firstly, we need to train a dense model, and then we need to remove some weights to produce a sparse model. And then we need to do the fine-tuning to recover the performance loss due to the weights removal. So in this process, we cannot use it directly in fact-based learning because if we do the pruning on server cannot perform it because in fact-based learning, server does not have access to the raw training data for the fine-tuning process. And also for clients, so quite often we want to do fact learning. Clients are IoT or mobile devices, and they are resource constrained to perform the fine-tuning. So these are the requirements for this model pruning process for fact learning. Firstly, we want to reduce the size of a global model transferred from the server to the clients. And secondly, we want to reduce the size of local updates from the clients to the server. And we do not want to reduce much computation overhead at clients. And also we want to achieve comparable model performance with the dense model trained in vanilla fact-based learning. All these requirements are under assumption that in fact learning server cannot access to the raw data due to the privacy concerns. So this is our overview. We propose complement sparsification. So firstly, complement sparsification starts from vanilla fact-based learning, where the clients train a dense model and the server aggregates the client's models from the clients. And then we want to have the server to create sparse models. And this process can be simply remove the low magnitude weights and send the sparse models to the clients. And in this way, the model transferred from the server to the clients are reduced and the communication overhead is reduced. And then we want the clients to train from the global sparse model received from the server. And from the training, we can produce a new dense model, but we only send the weights that were original 0 in the global sparse model. So in this way, the communication overhead from the clients to the server is reduced, and also the computation overhead of clients is minimized. So because in this process, we have the global sparse model and the client sparse model complement to each other. And then we can aggregate them together to produce a new dense model, a new global dense model. And this new, with this new dense model, we can repeat the step number 2, which is remove some low magnitudes again on the global sparse model. And in this way, this process can repeat, and then we can eventually update all the weights over time. So in this server aggregation process, we also want to amplify the client sparse model a little bit to make sure they will not be pruned away in the next round, and we can produce a new set of the weights to be pruned away by the server. So in this way, all the weights of the model can be updated over time, and then we can achieve a comparable performance as vanilla feather learning in this process. So now let's look into the details. So in this system, we have n clients and 1 server. And in the initial rounds, the clients train with their local data and produce dense local models, and send the local models to the server, and the server can simply average them and produce a global dense model. And then the server can do the pruning by removing some low magnitude weights from the dense model and produce a global sparse model. So here, the remaining weights are marked as green, and the removed weights are marked as red. So this global sparse model is also associated with a pruning mask. And then the server sends the global sparse model to the clients, and the clients can fine-tune the global sparse model received from the server with their local data again, and produce new dense models. And then the clients apply the inverted mask to the client's dense model to produce client sparse models. So this inverted mask can be either received from the server, or can be produced from the global sparse model by the clients. So in this way, we have new sparse models from the clients, and the clients can send them to the server. Server can average them, and then because this client average client sparse model and the global sparse model of previous round complement each other, when we aggregate them together, we can produce a new full global model. So in this process, which is not shown in the animation here, is that we can amplify the client's model a little bit to make sure the weights can remain. So make sure the weights will outgrow other weights. So in the next round, and when we apply this low magnitude pruning again on the global sparse model, and we can produce a new global dense sparse model with a new pruning mask. So in this way, every round we can have a different set of ways to be updated through, and this communication process all use sparse models bidirectional between the clients and the server, and also the computation on the clients is very little. Just apply the inverted mask on the dense model. So in the next 2 slides here, I will show you some technical insights, and the next slide will be some analysis of this process. So in this process, we in feather learning, we have clients as the server are in complementary relationship. As we see, the clients usually perturb the global model to follow their local data distribution, and the server conciliates the client's models to capture the global data distribution. So in complement sparsification, we take one step ahead and uses complementary sparse models in this process. So in this process, we have low overhead in computation and communication. And here we have the clients to perform implicit fine-tuning instead of explicit fine-tuning as a regular model pruning in centralized learning. In order to update all the weights over time, we have clients and the server aggregates the complementary subsets of the models to produce a new dense model every round. And this process is we use an aggregation ratio to ensure the previous pruned weights will outgrow others, and all the weights can get updated over time. So this is some little bit of analysis to show this process complement sparsification approximates vanilla fine-theory learning. So this is our complement sparsification aggregation function here. We have a prime to denote the sparse model, and the weights without prime is a dense model. So as we see, so to produce a new global dense model, we aggregate sparse server model together with the weighted sum of the sparse client's model with the aggregation ratio to amplify the client's outcomes. And here, because we have the every round, the new dense client model mostly updates the zero weights in the sparse server model. So when we subtract it, it zeroes out the non-zero weights in the sparse server model, so which approximates the sparse client's model here. And then we can take the client learning rate out, and then it becomes a gradients on the local data for the clients. And essentially, because we have the global sparse model approximates the global dense model, and here we get the vanilla fine-theory learning aggregation function. So here, this function here, we can see the overall learning rate is a learning ratio together with a client learning rate. So in the next few slides, I will show you some evaluation of this process. So we implemented a complement sparsification with TensorFlow and Flower. We used the two data sets. The first one is the Twitter data set, and the second one is the feminist image data set. We have two models used. The first one is the sentiment analysis, which classify a Twitter message into negative, positive, or neutral. So in this model, we use the pre-trained distilled BERT and the two dense layers. This is a relatively small model. And the second model is an image classification model. We use two CNN layers and the two dense layers to classify the image in feminist data set to one of the 62 classes. So this model, we consider it as a relatively larger data set. We have the larger model. We have the two models to check if there are any difference. So we use complement sparsification process on different size of the models. We have the two baselines here. The first one is PQSU, which includes a structured pruning model quantization and a selective updating. The second one is a prune FL, which firstly prune at the selected clients and also do the for future further pruning during the further learning process. And it can update the model size to minimize the estimated training time. So in this slide, I've shown you some comparisons results between complement sparsification, vanilla fine-theory learning, and baselines. We have the two applications here, and the blue lines is our process, and the red line is vanilla fat learning. The other two lines are the baselines. As we see from the two figures, our process complement sparsification approximates vanilla fat learning. And one interesting observation here is through this smaller model. So in the initial round, the performance dropped a lot in our process. This is due to we remove some weights from the global model. However, this process can gradually recover from the performance drop. Eventually, through the training process, our process can still approximate the vanilla fat relearning performance. And also, when we zoom in the learning curve, as we see, our process has a lower fluctuation than vanilla fat relearning. This is a benefit for model selection when we do not have a representative validation data set. So with our process, it's safer just to use a current random model. However, in vanilla fat learning, especially we do not have full participation from all the clients. The performance fluctuates a lot. And if we do not have a validation data set to select the best model, it's quite possible if we just use the current model of the model currently run, it will not perform well. So in this slide, I will show you the effectiveness of our process by using the lower overhead pruning. So we have two applications. The blue lines is our global sparse model, and the red lines is a aggregated dense global model. As we can see, global sparse model outperformed the aggregated dense model with less fluctuation. And this indicates that even simply removing some low magnitude weights can effectively eliminates the noise in the aggregated model. So in this slide, I will show you some communication and computation cost saving from our methods. We run experiments over different server model sparsity here. And then we check the average client's model sparsity over the communication runs here. And also in these two tables here, we also compute the flops saved on the server because we use a sparse model in our process. So here in our process, the server sparse model and the client sparse model complement each other. However, in practice, we observe that not all the weights get updated, not all the zero weights get updated by the clients. And the clients just update a smaller portion of the complement part of the server sparse model. That's why the client model sparsity is always low as 93% sparsity. So from these tables, we see in our process, we can save communication between the clients and the server bidirectionally, and also save the computation on the device. So in this slide, I show you the accuracy versus different server model sparsity we run over the experiments. And we see with different models, server model sparsity, we can achieve a good model accuracy. However, there is a trade-off between the server model accuracy and also the versus model performance. And we can choose the model sparsity, desired models, server model sparsity for our application. Okay, this is the conclusion. And our process complements sparsification is a practical, low overhead model pruning for feather learning. It helps adoption of feather learning on resource-constrained mobile and IoT devices. And in this process, we have the server and the clients create and exchange sparse and complementary subsets of the dense models, and we achieve up to 93% bidirectional communication overhead reduction, and about 49% computation overhead reduction on device. We achieve a comparable model performance as a vanilla feather learning, and also we outperform the baselines. Thank you.
Thanks so much. It was a great talk. I was wondering, this work was presented back in February, and so that means you probably submitted it earlier in late last year. And so since then, how have you pushed this work forward? Have you gone into a different direction, or have you been advancing it? Maybe thinking about how you can apply it to different settings? I'm just curious.
Right now, after this work, we haven't think about how to extend it. But right now, I think this work right now is just a framework, not much fancy things happens in this process. I think a lot of things can be done. For example, personalization can be added, and we can tweak some small things to improve this process. For example, cool. The pruning process right now is simply remove the low magnitude weights, and it can be extended to different methods to do the server model pruning without server data. That's one way we can improve it. A better way, not just to simply remove the low magnitude weights. Yeah, that's also possible.
Very interesting. Yeah, and then what are you most excited about using or expanding federated learning in general? Is there a particular direction that you want to see it advance?
I think one thing missing here is in feather learning. Right now we assume the data to be static. It means data do not change over rounds. So for all the clients, we put all the data together, and just one data set, the client's data do not change over time. But in practice, in real life, we usually, it is not the case. We want to perform the training as the client's collecting data, not just the static data. So when we have a dynamic data set, we may also do not want the data to keep accumulating on the clients. Maybe due to the resource constraint, we do not want the client to leave so many data on the device, or on the mobile or IoT devices, or so in that way, it's one thing I think in feather learning is a lot of people, not too much work done on this direction. It will be interesting to work on this direction.
That's really interesting. Yeah, I can see that. You might even encounter situations where when you select some clients, those clients might have data from the old distribution, depending on how fast the data arrives to them. Well, really interesting. Yeah, thanks for that food for thought. Really, very fascinating. Thank you for the talk. We're now going to move on to our next speaker,